All right, welcome back, everyone, to part two of Simon's problem. In this lecture, we're going to talk about the quantum algorithm to solve Simon's problem. In the previous lecture, we talked about the classical algorithm to solving Simon's problem. And you'll remember that the classical algorithm takes 2 to the n queries to a classical oracle to solve the problem, which is unfortunate because that's exponential time and it grows really, really fast and blows up quick. So we would like a better alternative to that. Before I discuss the specific quantum algorithm that solves Simon's problem here, I want to think about the Jorge and the Deutsch Jorge Hosa algorithm rather, and I want to think about a pattern that's kind of emerging here. Um, if you'll recall, in all of these kinds of algorithms, we have this same kind of thing popping up time and time again, and it looks like this, right? We have this, and then there's some sort of term here, and right? So the -1 and the term generally is going to take either 0 or 1 as a value. Depending on which value it takes, the sign is going to be flipped or it's not going to be flipped. Now, what these things are phases. Remember when we talked about quantum mechanics before, we talked about the fact that we're dealing with matter waves and we're dealing with phases, and we have this constructive and deconstructive interference. I think you guys probably remember that, but in case you don't, um, we have waves now. Let's say we have like a cosine wave here. If both these terms are +1 + 1 or -1 - 1, they're basically two waves are kind of stacking up and they're kind of reinforcing each other. But if they're -1 and +1, you remember we have these sums and the terms kind of go out. And this sort of acts as a filter. It filters out all the terms that destructively interfere and they don't show up in the final result. And then all the terms that do constructively interfere are the ones that are the only ones that make it through this filter step. And we usually implement this with a Hadamard gate. So you'll notice that this is the kind of quantum difference in physics that we're exploiting. You don't see this in classical computers. You're not dealing with waves, you're dealing with bits. So this is sort of the essence in the early quantum algorithms of the pattern people started noticing. That if we line these phases up right and we exploit the mathematics of wave phases just right, we can create these sort of filters that filter out all but the correct results. And we can do this in a way that cuts down the queries very, very large because waves and this quantum parallelism allow us to explore a very large solution in state space with just one wave, right? With which is one query. So that's kind of what we're doing here. So with that said, kind of bear this in mind as we go through the solution to Simon's problem, also known as Simon's algorithm. And let me just show you the circuit that we're going to be using and the registers that we're going to initialize here. So the two registers we're going to initialize look like this. They're just N zeros. That's all they are. Um, and the first one we're going to take through a Hadamard gate. The second register we're going to do nothing to. And we're simply going to then put this through a quantum oracle. And I'll explain what the quantum oracle does when we get to that step. And then we're actually going to take this through here, take a measurement here. We're not going to measure this quite yet. We're going to put it through one more Hadamard gate, and then we're going to measure it. All right, so that's what we're going to be doing. So let's go through mathematically the details here. We'll start inside 0, and we'll start simply with 0 to the n and 0 to the n. Um, and you know what? I should really briefly go over the problem we're trying to solve again here. Recall that in Simon's problem, we have a function, f of x. And we have a string, an n-bit string of zeros and ones called s. And f of x will have a periodicity to it if you have two values that you put into it, x1 and x2. Let me just write this down actually. You have f of x1 will be equal to f of x2 if and only if f of x2 is equal to x1 dot s. Where, as you recall, this kind of dot function, all that really means is we take x1. Sorry, there shouldn't. This is confusing nomenclature. Let's call this y. All right, so fx, fx, xy, because I'm going to be using the subscript 1 to refer to the bits. So x1 is the first bit in the x string of n bits. And s1, bitwise XOR, the second bit of x, and the second bit of s, XOR, dot, 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 all the way out to the nth term. Okay, so that's all that dot really means. So we're going to be seeing that in, I think, psi of 2. We'll be seeing that kind of dot there. So this is our initialization state here. We have one register with n zeros in it, and the second register has, again, 0 n's in it. N zeros, rather. Now, after psi 1, we're going to take it through a Hadamard gate. And the Hadamard gates change the phase, which, remember, keep that in mind, we're exploiting these phase differences. That's the crux of these early quantum algorithms. So what we're going to have here is, well, let me just do it out without the fancy mathematical notation, because it kind of obscures what's actually happening here. Remember what Hadamard gate does. It takes a 0 to this. So we're just going to have n of these. That's all we're going to have, right? That's it. That's all we got. Just n of those. And what the fancy mathematical formalism is actually going to say is this. Right? And each x is an n-bit string. And we're foiling. So we take this times this times this times this times this times this. So our first term is just going to be 0, 0, 0, 0, n zeros again, right? Our second term, this times this times this, and the last time maybe we hit the 1 instead. So it's going to be 0, 0, 0, dot, 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 and term will be 1. Right? So that's all we're kind of dealing with here. We're foiling out these terms, and x is going to be a symbol for each one of these foiled out terms. And there's going to be sum of x's, because that's just the rules of how you foil things, right? That's all. All right. Scroll down a bit. So just the sum of these x's here, and you still have your second register untouched. To the n, which is good. In the second step, we're now going to be using this quantum oracle. And the quantum oracle is simply defined by this. It takes in this state, and it outputs this state. That's just what it does. Don't worry about the implementation for now. There are possible implementations of this. It can be done. That's all we need to worry about. For the purposes of understanding this algorithm, we don't need to know exactly how this implementation works. So we have our sum here from x equals 0 to 2n minus 1. And that's, by the way, that's what the second register is for. It's for storing these f of x's. So this is the part of the algorithm where it actually kind of comes in. Up until now, it hasn't been used. All right, so we have now sum of x's and f of x's. And if you recall, at this point in the algorithm, we want to make a measurement. We want to measure, oh, sorry, we want to measure the second register, not the first one. We want to measure the second register where f of x is. Now, remember, this is a sum. This is a superposition of different states like this. So this is a superposition of x times f of x's summed all together. So when we take a measurement, what that actually means is that it will collapse into one of these states with the probability that's their coefficients. And in this case, the coefficients are all the same. So it's equal probable that we will get each possible state here. So let's make a measurement and see what happens. What's going to happen is we're going to get f of x of 0, where x of 0 is one of these x's. And each of these are equally probable. None of them is favored probabilistically. And what that state is going to do once we get that measurement, then we will be in the state of psi of 3, I believe we're up to now. Double check. Yeah, we're up to psi of 3. We're up to psi of 3, so psi of 3 equals, we have x of 0 out here now because we've measured and it's collapsed. And here, we have a superposition of x, but also recall the condition of the function f of x of 0 is that x of 0 plus, or dotted rather, with s is also a solution. Recall that. So that means either of these x's could have satisfied this function, right? X of 0 and x of 0, so if x could also satisfy this function because this equals f of x of 0 by x, right? So we actually now, the x's, because of this measurement, the x's have been put into a quantum superposition of either this or this. And of course, there's a normalization constant of 1 over square root of 2 because it's equal probable that can be in each position. So now we actually have something interesting. Now we have a state that we can kind of look at and say, okay, if we make a measurement now, we're not going to learn anything. But what if we put it through a Hadamard gate and try to do something clever to kind of exploit these phases that we've been talking about and dealing with? All right, well, let's give it a shot, right? Let's put it through a Hadamard gate and see what happens. And of course, obviously, I wouldn't be wasting your time. Something interesting does happen. So we put it through a Hadamard gate, and we get this kind of thing. All right, yeah. So the phases, of course. And we get so that y plus the phase, I believe it's s dot y, right? S dot y is the second phase. No, it's xo bitwise phase, right? Right. Times y. Okay, now we're looking good. Because there's a pattern here. Um, if we get this, the phase is deconstructively interfering, then this just will go out, right? This will just go out. But if we get them of the same sign, then they'll constructively reinforce and add up. So again, this is the unique advantage of waves that we get in quantum mechanics, is we can kind of use these phases and these interferences to kind of create a filter. And this is the filter step, remember. Um, I wanted you to keep this in mind, that we have this kind of filter step. This is the one. So at this stage, um, if s dot y equals 0, then these phases will line up. Yes, these phases will line up. Right. S times y. Yep. Okay. And the other possibility is that s times y equals 1, in which case we'll get +1 -1 or -1 +1, and the phases will cancel out. So the only y's that will survive in our final quantum superposition will be y's that satisfy this property. Those will be the surviving y's in our quantum superposition. I equals 0 through whatever. Through n. I'm not sure how many there are. But the idea is that now when we measure, we'll get one of these y's. And when we get one of these y's, we know it has this relationship. Or 0, sorry, 0, 0. We know it has this relationship. So if we do this n times to get n different y's that all have this relationship, we eventually get n equations that look like this. And now we can use something like Gaussian elimination to actually solve for s. that's what we wanted to do. So great. We sped this up to polynomial time. Um, Linear time, actually. This runs in linear time, whereas classically, this ran in exponential time, which is horrible. So this is really great. This is the quantum advantage, and we've seen it kind of for the first time, a true complexity class speed up quantum advantage. So hope you've all enjoyed, and that's Simon's algorithm. So now that we've kind of noticed this periodicity, we're going to be looking at quantum Fourier transforms next time, because this is kind of the secret sauce to a lot of quantum algorithms, is this the fact that waves are really good at sniffing out periodicity. They're really good at it. Think about diffraction gradients and things like this, right? Waves are great at that. So next time we're going to do the classical Fourier transform just to introduce. Then we're going to do the quantum Fourier transform, and then we can get into quantum factoring and stuff like that, which is really fun.